So for what we have on page 249, okay, so you have y is equal to k of x. Okay, we have is equal to 2 times, okay, the square of x minus 3 minus 2. Okay, so we have, again, we have k of x laid out in vertex form. So you have that a is equal to 2. And again, from x minus h, I'm able to get the theoretical or the general representation of what defines the axis of symmetry, where I have x is equal to h, and we have x minus h is represented by x minus 3. So if I set this to 0, I have x equal to 3, and so I have x is equal to h is equal to 3. And for what we have for the value of k, okay, we have the subtraction of 2. So we have that k is equal to negative 2. And so just looking at what we have throughout the parts, okay, so we got, we have that a is equal to 2. And we have that a is positive. So the graph is going to open upward from the vertex. And again, not going from part A to part B, but to part F. Okay, part F is asking for the axis of symmetry. And again, the axis of symmetry, we have x equal to h. And in this case, we have that x is equal to 3. Now for part B, okay, we're going to have the location of the vertex, where the general coordinates will be in the guise of h and k. Okay, and so we'll have the ordered pair to be 3, negative 2. Now, for what we have in the case of the intercepts, okay, so we have with the x-intercepts, okay, we have x0, and again, in solving for x, so I'm looking at setting y, or in this case k of x, equal to 0, and solving for x. So again, for that which represents y, I'm going to set equal to 0. So we have 2 times, okay, the square of x minus 3 minus 2. And in looking at solving for x, okay, what I'm going to do here, now I could square out x minus 3 and set up a trinomial and like use factoring or the quadratic formula to solve for x. But what I'm going to do here instead is to create a pathway to utilize the square root property of equality. So I have 2 is equal to 2 times, okay, the square of x minus 3. And if I divide the equation by 2, okay, so I had that 1 is equal to the square of x minus 3. And just switching sides here. Kind of go from b is equal to a is equal to b format. Okay, so I have the square of x minus 3 is equal to 1. And just carrying on for what we have with the square root property of equality. So again, that property states that if x squared is equal to p, x is equal to plus or minus, okay, the square root of p. And so here we have x represented by x minus 3, so that is squared. And if I go from second order to just first order, so we're going to have x minus 3 is equal to plus or minus, okay, the square root of 1. So we have the x minus 3 is equal to plus or minus 1. And so for the x-intercepts, okay, so if I separate the plus and the minus 1, so we have at the lower end, x minus 3 is equal to negative 1. And for what we have at the upper end, okay, we have x minus 3 is equal to 1. And so we have an isolating x in both equations. And we have in both equations we add 3 to both sides. Okay, so if x minus 3 is equal to -1, okay, we have x is equal to 2. If x minus 3 is equal to 1, okay, so we have x is equal to 4. And so we're going to have with our x-intercepts, okay, have x equal to 2 and x equal to 4. And if I display in coordinate fashion, we're going to have 2, 0, as well as 4, 0. And for what we have in the case of the y-intercept, okay, so for what we have in the case of the y-intercept, okay, so we're turning the tables in terms of what to solve for and what to set equal to 0. Okay, now in the case of this particular function, again, k of x represents what we have for y. And if I set x to 0, so y is equal to k of 0, and that's going to be equal to 2 times the quantity. Okay, so you have 0 minus 3 raised to the second minus 2 0 minus 3 is -3. And the square of -3 goes to 9. Okay. And so 2 times 9 is going to be 18. And 18 minus 2 becomes 16. So we're going to have a y-intercept. So you have y is equal to 16, and in ordered pair terms, we come out to 0, 16. Okay, so just sort of taking a step back. So this is the equation we started out with. The layout was already in vertex form. So we have a at 2, h at 3, k at -2. Again, a is positive. The graph opens upward. And it's going to open up from the vertex, which we have at 3, -2. And the x-intercepts, we have 2, 0 and 4, 0. And the y-intercepts, okay, we have at 0, 16. Now looking at what we have in the visual layout, okay, so we have this, okay, so I'm going to okay, so again we have y, and this representing k of x is equal to 2 times the square of x minus 3 minus 2. Now it's going to zoom in a little bit. So we have with our points, again we have the y-intercept 0, 16, the x-intercepts at 2, 0, 4, 0, and the vertex we have at 3, -2. And again you have this this line here passing through the middle, and that is the axis of symmetry. It's not the graph itself, but it's just a vertical line that evenly splits the halves of the vertex. And if you notice with the axis of symmetry, both halves will be equal in distance from the dividing line. So from the vertex, if you notice, okay, we have, if you look at it from the vantage point of counting squares, 4, 0 is one space to the right, 2, 0 is one space to the left. And if I go up, let's say for 0, 16, you got like 3 squares, and each square is like 2 units. So you have like -2, -4, -6. So you have 6 units to the left. And if I mirror across and go like 3 squares or 6 units to the right, so you got 2, 4, 6. And so we're going to have, if you were to identify an additional point without using the equation and just utilizing the axis of symmetry instead, you can have an additional point with 6, 16. And these 5 points would be again, 5 among infinitely many other points that would make up the graph of this particular quadratic function. All right, now in what we have with item number 12, okay, and we have in this one, we have another quadratic function. Okay, and this is also provided in vertex form. So again, we have y is equal to r of x. And for what we have in the function given, okay, in number 12, okay, so we're going to have r of x, and we have is equal to, and that was 1/2 of x plus 2 quantity squared. Okay, so in identifying a, b, and c, so here a is at 1/2, and for the h value, okay, so x minus h is represented by x plus 2. And if I set this to 0, then we have that x is equal to -2. So you have x is equal to h is equal to -2. And for the k value, notice that nothing is added or subtracted after 1/2 of the square of x plus 2. So we have a void here. So right away, we're going to have that k is equal to 0. And just for the items, once again, for the direction that the graph opens, okay, again, that's contingent upon the sign value of a. So with a at 1/2, okay, 1/2 is positive. So the graph is going to open upward. And for what we have in the case of the axis of symmetry, again, your h value we have at -2, so we're going to have that x is equal to -2. And in the case of the vertex, okay, so h is at -2, and notice that k is 0. And this vertex is going to turn out to be an x-intercept. And now looking for the intercepts. Now the x-intercept is going to have an element of repetition to it. Okay, so again, we're setting what represents y equal to 0. Okay, so again, we'll have that 0 is equal to 1/2 of the square of x plus 2. And say if I take care of the fraction multiplying both sides of the equation by 2, okay, so 2 times 0 is 0, 2 times 1/2 is 1, so we have 0 is equal to the square of x plus 2. And again, just like what I did earlier, okay, I'm just going to switch the sides here, having the variable expression on the left and the constant on the right. And again, we have with the square root property of equality, so if I go from the square of x plus 2 to just x plus 2, okay, so you have plus or minus the square root of 0. And guess what? Okay, there's no positive or negative 0. Okay, it's just going to be 0. Now there is such a thing as like small infinitesimals, like positive and negative, like 0.0000, but that's a different topic. And so there's going to be only one x value here, and that's x is equal to -2. And it's going to turn out that for the x-intercept, we have x equal to -2, and in coordinate terms, that is going to be -2, 0, which we have already for the vertex. Right. And as for what we have regarding the y-intercept, okay, so we have that y is equal to r of x, where x is going to be set to 0. So r0 is equal to 1/2 of the square of 0 plus 2. And for what we have in following through, okay, so you have 0 plus 2 is 2. And 2 squared is going to be 4. And so we have 1/2 of 4 is equal to 2. So our y-intercept is going to be at y is equal to 2. And we have as an ordered pair. Okay, when we come out to 0, 2. All right. So just looking at what we have from a visual standpoint. So this is a case of where the vertex and the x-intercepts are one and the same. So right now we have just 2 distinct points identified. Okay, and now, and taking what we have and just looking at this function from a visual standpoint. Okay. All right, so you have the vertex and the x-intercept to be one and the same. Okay, so, and here the graph of the parabola, okay, opens upward, and again we have a y-intercept at 0, 2, and again we have with this particular axis of symmetry, again we have an x equal to -2, and the axis of symmetry always passes through the vertex. And so if you were to go up, have other points like -4, 2, 0, 2, -8, 18, 4, 18. And, okay, so if you notice going up from the vertex, okay, you have 1 square space to the right, 1 square space to the left. Okay, so you have 0, 2, -4, 2. And with each square space, like in increments of 2, okay, notice we have level with each other. You have at y is equal to 18. So you have, like with 418, you have 1, 2, 3 spaces to the right as we go from, or so say, what's going to be 6 total spaces. And we have, in terms of the square sections, have 1, 2, 3 square sections to the left, or all in all 6 spaces to the left. So you got -8 is 6 to the left of -2, 4 is 6 spaces to the right. So you have, again, symmetry throughout from top to bottom. So you have these points again to be among infinitely many others that will make up the graph of r of x is equal to 1/2 of the square of x plus 2. All right. Now, for what we have in the case of the items, where we have translating from standard form to vertex form, and we have for these quadratic functions, okay, and we'll look into numbers 17 and 20. And in the case of number 17, okay, so we have a function p of x, and this one we have given as 3x squared minus 12x minus 7. Okay, so this is going to be the standard form. And if I convert to vertex form, now in comparison to what we looked at the other day, okay, so we got for this one, okay, so if I separate the variable terms apart from the constants, okay, now in comparison, what the other day we had the first terms to be x squared, but now we have a coefficient other than 1 in front of the leading term. And I'm about to mention something regarding this. And especially in terms of how to follow through. So we have a 3x squared minus 12x minus 7. Okay, so if I separate, so if I group together 3x squared minus 12x, and I have followed by the subtraction of 7. Okay, now I want the first term, if I'm looking at the completion of the square, I want the first term to be in the parentheses to be x squared. Now we got the 3 out at the front. So if I go ahead and factor out 3 and have this outside the parentheses, okay, so we have p of x is equal to, we have 3 times, and we have the quantity of x squared minus 4x, and we have followed by the subtraction of 7. You can always go back and check 3 over x squared minus 4x. You have 3x squared minus 12x, and you'll have minus 7 to follow. Now, the first term inside the parentheses is going to be x squared. So this is going to be our backdrop to complete the square. And again, so I'm going to add a constant to make whatever I have to add to x squared minus 4x to lead to the formation of a squared trinomial. So we have in the crossover to complete the square, okay, leading term inside the parentheses, we have x squared. And if I take what is next to x in the stage of completing the square, again, I take half of what is next to x and then square. So here I have negative 4, divide by 2, so we have negative 2, and squaring out negative 2, okay, so this will become 4. So here I'm going to have 3 times the quantity, and I have x squared minus 4x, and I'm going to add 4 inside the parentheses. Right, now I'm going to try to create a balance, and what is happening is that as I'm adding 4 inside the parentheses, I'm not adding just 4 at the front, I'm actually adding 3 times 4. So you're looking at the overall situation. So at the front I have 3 times 4, so by adding 4 inside the parentheses, I'm actually adding overall the value of 12. So I'm creating a surplus of 12 units, and so to undo the surplus, I'm going to take away 12 at the back. So we're now going to have p of x is equal to 3 times, okay, the quantity of x squared minus 4x plus 4, and negative 7 minus 12, okay, that is going to be negative 19. And you can sort of double check, okay, so to make sure everything is in balance. Okay, you have 3 over x squared minus 4x, you have 3x squared minus 12x. 3 times 4 is positive 12, 12 minus 19 is at negative 7. So your k value is going to be at negative 19. And then we have, in terms of writing p of x in the vertex form, okay, so you have 3 times. And for the binomial now, x squared is going to be the square of x. And for the constant, I need to fill in, well, guess what? You're going to fill in with the number that you squared just moments ago. In this case, we squared out negative 2 to initiate the completion of the square process. So this is going to be transported over to finalize what we have for the vertex form. So we had that p of x is equal to 3 times the square of x minus 2, followed by the subtraction of 19. And so this is going to be the resulting vertex form for this same function. Okay. Now, so we'll look at number 20. And for this one, okay, if we take with d of x, okay, so you have the standard form. And here we have negative 3x squared minus 9x plus 8. And just like what I did earlier, I'm going to separate the variable terms apart from the constants. And the variable terms happen to both be negatives. And just like before, okay, I want the first term inside the parentheses to be x squared. And if you notice, you have the leading coefficient is at minus 3. Okay, so if we look at factoring out negative 3, okay, so you're going to have here d of x, okay, again we have is equal to negative 3. Negative 3 into minus 3x squared, that's going to be x squared, followed by plus 3x, and followed by the addition of 8. Okay, so after factoring out negative 3, again the first term in the parentheses again is going to be x squared. So we're going to have, once again, the capacity to complete the square. And there's going to be a bit of a different dynamic that's going to be carried out for in the case of the completion of the square. Okay, we're looking at taking half of an odd number. Okay, so I'm taking half of 3 halves and then squaring out. So for completing the square, I'm going to take the square of 3 halves. And 3 halves times itself is going to be the fraction 9/4. And taking what we have for d of x, okay, so you have negative 3 times the quantity, okay, so you have x squared plus 3x we have plus 9/4, and we have plus 8, and remember, okay, you want to balance between what's at the front and what's at the back. And in this particular case, as I'm adding 9/4, I'm not adding, instead I'm applying at the front what amounts to negative 3 times 9/4, which is negative 27/4. So I'm looking at a negative at the front, so I'm essentially subtracting by negative 27/4 at the front, so to override what is a formed deficit, I'm going to add 27/4 at the end. And so for what we have in the case of 8 plus 27/4, and just sort of moving to the side here, so you have like 8, you have like 8 over 1 plus 27/4. And of course, 4 is going to be the least common denominator. Okay, so as fourths, okay, 8 is going to become 32/4. We have plus 27/4. And the sum of these numbers, we're going to have the non-integer value of 59/4. So we're going to have d of x. Let's see. Just a moment. So you have for d of x, so you have negative 3 times the quantity. So we have x squared plus 3x plus 9/4. Now 8 plus 27/4. Okay, that is going to be at 59/4. And we'll have for the vertex form, okay, so we have -3. And again, for the binomial, okay, so again, x squared is going to be the square of x. And that which we squared out to initiate the completion of the square process. Okay, so we have it 3/2. So we'll have for the vertex form, we'll have -3 times the quantity of x plus 3/2 to the second, followed by the addition of 59/4. And that'll be the vertex form. All right. You could, yeah. Yes. It will come out as 14.75. Yeah. So as a decimal or as a fraction, it'll still be the same. Okay. Now, in terms of what we have for other items, okay, and we have working with polynomial expressions, and these expressions are not, they can include quadratic functions, but they can also include, they can also be functions of other types, you know, whether linear or cubic or any other degree. And now, for what we have in the case of forming polynomials, okay, so you have forming polynomials from zeros and multiplicities. Okay, and I'll show you what I'm going to be looking into now. There are some parts that will emphasize like the factored form of polynomial expressions, and then there will be some other aspects where it'll be looking into the expanded form of polynomial expressions and working with zeros and multiplicities. Okay, now we'll look into multiplicity and application as we go a little bit further into this part. But I'm going to go ahead and apply a definition here. Now for the multiplicity of a zero, okay, now multiplicity, okay, you're looking at exponents. And for the multiplicity of a zero, okay, that is going to be the degree to which the factor corresponding to that zero is raised when the function f of x is expressed in factored form. So, okay, so this is going to be multiplicity, and we'll look into a case in just a moment. Okay, but let's say that just as examples here, if we're looking at determining a factored and expanded form of f of x given, let's see, we have for the following, and I'm just going to start out a case where the number of zeros and the degree will be the same. See, we have for the zeros, and we'll say that we have like -1 and 5 say that the degree is going to be equal to 2. So you have the number of zeros. Okay, we have 2 of them with -1 and 5, and the degree is going to be at 2. And now for establishing a factored form, okay, so you can think of this like working backwards. Whenever we had problems with the zero product property, say if you have like a 0 or a solution of x to be x is equal to -1. If you step back and write this equation and set in terms of where it is equal to 0, kind of like working with solutions and putting in like the standard form of a quadratic equation, but where we're working with a linear set of terms instead. Okay, we have the x plus 1 is equal to 0. So if x plus 1 is equal to 0, x equals -1, so -1 is a 0. And for 5, okay, so if I have like x is equal to 5, we can say that this is going to originate from a factor in the form of x minus 5. Okay, so for what we have in the case of the factored form of f of x, so for the factor form of f of x, again we have the f of x is equal to, and again for the factors we have x plus 1 and from 5, okay, we have x minus 5. Okay, so this will be a factored form of f of x. We have x plus 1 times x minus 5. Now for the expanded form, this is just foiling out what we have in the terms. Okay, so for x plus 1, quantity times the quantity of x minus 5, so I have x times x is x squared. Outside product, we're going to have at -5x. Then we have plus x for the inside product, and the last product is going to be at -5. And so we're going to have for the expanded form, we're going to have upon combining the middle two terms. So we're going to have x squared and -5x plus x. Okay, so that is going to be -4x. We have -5. Okay. So again, let me just mention, okay, so we got with x squared minus 4x minus 5. Think about if you were to set this equal to 0. Think of this like quadratic equation to solve for. If I were to take x squared minus 4x minus 5, set equal to 0, and then factor, so I would have x plus 1 and x minus 5. and then set each of the factors to 0, but I would come back to x equals -1 and x is equal to 5. And again, the degree of this polynomial is 2, and the expanded form defines this for the highest order degree, or I say the highest order term that we have in x is going to be x to the second. All right. Now where multiplicities can come in, and let's say if we have for the zeros, and we'll say that we have it's going to mention, okay, say we have for the zeros, okay, we'll say that we have 0, let's say we have a multiplicity of 3. Let's say we have another 0, so we have -2, which is going to have a multiplicity of 2. And then we're just going to have the number 1 as a 0. And the degree of this polynomial is going to be at 6. Okay, so if the multiplicity is not specified for the respective zeros, just regard that as a multiplicity of 1. And the total degree would be the sum of the multiplicities. So you have like 0 with 3, and then got plus 2 is 5, and then 1 with a multiplicity of just 1. That is going to come out to 6. Okay, now in terms of the factors, now again, think like for x is equal to 0, I would have x. And if I think of x equals -2, I'm going to have this to stem from x plus 2. And with x equal to 1, I can say this is going to stem from x minus 1. Okay, now where the multiplicities come in, now from 0 I have x, but I'm not going to have just x. Since 0 has a multiplicity of 3, I'm going to have not just x, but x raised to the third power. And with -2, okay, I have x plus 2, but since -2 has a multiplicity of 2, this binomial is not going to be just x plus 2, but it's going to be x plus 2 raised to the second power. And we have with 1, okay, there's no raised multiplicity, so just if it is not explicitly provided, the multiplicity is just 1, so this factor here is going to be raised to the first power. So we have as a factored form of f of x, so you have f of x is equal to x to the third times x plus 2 raised to the second, and then we have times x minus 1. Okay, so again, if you notice you have 3 zeros, but we have 6 orders, so the number of zeros and the degree of the polynomial will not match up. And if we look at expanding, and just taking what we have here, okay, so we have with f of x equal to x cubed, and we have times the square of x plus 2, times x minus 1, and you can do this in various ways. So we say we have x cubed times x plus 2 times x plus 2 times x minus 1. there are various ways you can follow through on this. And what I'm going to do, I'm going to do a little bit of clustering. Okay, say I'm just going to multiply the first two sets here, x cubed over x plus 2. Okay, I'm going to have x cubed times x, which would be x to the 4th, plus 2x cubed and for x plus 2 times x minus 1. If I go ahead and FOIL this out, I have x squared. We have minus x plus 2x, so that's going to be plus x. And 2 times negative 1 is going to be a negative 2. And if I multiply together, and this is where the geometric or the box method, okay, can come in rather nicely. Okay, so we have multiplying these polynomials. I can either have it set up as a 2 by 3 or a 3 by 2 formation. And I'll just let this trinomial be the column headings, and the binomial I have here to be the row headings. So just setting up a bit of a table here. Okay, so looking at, and we'll just do this column by column. So multiplying the corresponding parts here, x to the 4th times x squared. This is going to be x to the 6th. Now we have 2x cubed times x squared. So this will be 2x to the 5th. X to the 4th times x. This is going to be x to the 5th. Then we have 2x cubed times x. So this will be plus 2x to the 4th. And then we have, with the third column, okay, now we'll have negative 2 times x to the 4th. And the last product we have negative 4 times x to the 3rd. So just looking at what we have in the setup. Okay, so the highest order term is x to the 6th. And in 5th order, we have 2x to the 5th plus x to the 5th. So we're going to have 3x to the 5th. And if you notice, okay, we have 2x to the 4th and negative 2x to the 4th. Okay, so in essence, these are going to go out. And for what we have left standing, okay, we're going to have minus 4x cubed. So we're going to have in expanded form. Again, the polynomials can be of 6th order. So we have f of x is equal to x to the 6th plus 3 times x to the 5th minus 4x cubed. Okay. All right. Now, just kind of taking what we have in forming polynomials. Let's say for the first one, okay, we'll say we have our zeros per pound. We'll just say that we have 0, have the multiplicity equal to 2. Then we'll say that we have let's say 5 is also going to have a multiplicity of 2, and the resulting degree of the polynomial is going to be at 4. Okay. And see, well, just for the next few moments, let's see what we get for this particular polynomial in factored form as well as expanded form, given two zeros, both of which will have a multiplicity of 2, and where the expanded form is going to have the highest order degree in x to be at 4. Okay, just in the case of the setup, now for the big picture, you're looking at forming a fourth order polynomial. And if you're to think of an equation, not necessarily a quadratic equation, or maybe one that is quadratic in form, and you set it equal to 0, and you're looking at the zero product property, say for this polynomial, you're going to have two solutions in this one. One is going to be at 0, and the other one is going to be at 5. Okay, and so we're looking at taking like the solutions and kind of working backwards and configuring just what the original polynomial could be. Okay, and so just looking at the characteristics, now we have the 0 values of 0 and 5. So factors that would come to mind. Okay, so if I set x equal to 0, I already had the x factor. And if I set x minus 5 equal to 0, or if I had the x is equal to 5, we can have x minus 5 to be that particular factor. Okay, so I have x equal to 0 and x equal to 5, from which I have x minus 5 is equal to 0. So you will have with the respective factors. Okay. So I got x, but with a multiplicity of 2. We'll have not just x, but x raised to the second. Likewise, with 5 as a solution, now I have x minus 5. But again, since 5 has a multiplicity of 2, I have not just x minus 5, but x minus 5 raised to the second. So for what we have in factored form, so we have f of x is equal to x squared times the quantity of x minus 5 raised to the second. And looking at creating the expanded form of this, so we have for f of x, so we have in the intermediate stages, so you have x squared. Now for the square of x minus 5, you could square the binomial and form the trinomial right away. That is one approach, or just keep in mind that if I write in terms of multiplying, okay, so the square of x minus 5 is going to be x minus 5 times itself. And if I go ahead and say distribute x squared over x minus 5, and we have the f of x is equal to x cubed . minus 5x squared, and then we're going to multiply by the next x minus 5. And we're going to have in the layout, okay, so we have with f of x, okay, so we have x cubed times x, so this will be x to the fourth. Then we have the outside product, okay, so we have minus 5x cubed. Inside product, we also are going to have negative 5x cubed. And then we have with the last product, okay, so this is going to be 25x squared. So using what we have as the basis from the factored form, we're going to have for f of x in the expanded form, we'll have that f of x is equal to x to the fourth minus 10x cubed plus 25x squared. All right. And let me kind of cap this off. Okay, now we've looked at forming polynomials from given zeros and their multiplicities. Let's say if I determine the zeros and multiplicities, and we'll say that we have for f of x is equal to, and we'll just say we have x to the 8th, and say we'll have x to the 8th plus x to the 7th, and we'll say we have minus 28 x to the 6th. So if we're looking at taking what I have and breaking down, just going from this expanded form to the factored form. Okay, now if you notice, we have all these terms have raised powers in the variable x. Okay, and the greatest common factor here is going to be x to the 6th. So I have x to the 6th. And taking into this trinomial, okay, so we have x squared plus 12x minus 28. And here I can factor further. Okay, so I have x to the 6th. Now for x squared plus 12x minus 28, x squared factors out to x and x, and factors of negative 28, that will have a sum or difference at positive 12. More weight is going to be given to the addition than to the subtraction. So we have x plus 14 quantity times the quantity of x minus 2. And I'm just going to stress the degrees on this one. So this will be the factored form. I'm just doing a little bit of color coding here. So you have x to the 6th. We have x plus 14 to the 1st, since we don't have an explicit power, and x minus 2, okay, that is also going to be raised to the 1st. Okay, so in the case of the zeros, okay, so from x, okay, we'll have 0, and with the 6th order, okay, so 0 is going to have a multiplicity of 6. And from x plus 14, if x plus 14 is 0, x is going to be negative 14. And since x plus 14 is raised to the first, okay, this 0 is going to have a multiplicity equal to 1. And likewise, okay, we have x minus 2. Okay, we have a 0 at 2. And since the corresponding factor is raised to the first power, then we have just like negative 14. Okay, 2 is going to have a multiplicity of 1.